Good morning, everybody. My name is Daniel SANDNER. I'm in charge of measurements and test benches for the company Kuhn, and I will show you how we use our MTS tools to test our agricultural machines. To start, some words to introduce you the Kuhn company. Okay, Kuhn is a French manufacturer of agricultural machinery, which historical parent company is located in Saverne, in the east of France, near Strasbourg and the German borderline. So to define our field of activity, we can say that Kuhn is a manufacturer which offers one of the widest range of products on the market to be used as a tool with a tractor and some self-propelled machines. So our products and tools concern the plugging, the tillage, seeding and planting, fertilization, organic fertilizer, spreading, crop protection, landscape maintenance, shredding, hay and forage harvesting, and livestock bedding and feeding. About Kuhn's history, Kuhn is a very old company created in 1828 by Joseph Kuhn as a modest village forge. In 1864, Kuhn diversifies into production of agricultural machinery. And in 1946, after World War II, Kuhn was very weakened by the war and joined Becher-Gruyere Group, a Swiss industrial holding, and we have since that time the same shareholder. In 1987, Kuhn acquired his first external company, and it's the beginning of Kuhn Group, and we have since that time acquired 9 other companies. Some key figures on 2018, an average number of employees of 5,000 people, 2,800 in France, and turnover of approximately 1 billion euros, investment 55 million euros, and an annual production of 65,000 machines. This number has not a real signification because some of the machines are produced in 10 units, other one in hundreds or thousands. So 70% of our production is exported in nearly 100 countries on the 5 continents. Here you can see all the Kuhn Group facilities. So each factory in Kuhn Group is specialized in some family of products and has his own R&D organization. So as I told it before, the parent company is located in France, in Saverne, for hay and forage harvesting, animated tillage tools, and seed drills. Then we have 3 other companies on the west coast of France, which is Kuhn Huard for plugging, non-animated tillage and seeding, Kuhn Blanchard for crop spraying, Kuhn Oduro for livestock bedding and feeding, and some self-propelled mixers. 1 company in Geldrop for baling and wrapping, 2 factories in North America for for tools for the US market, 2 factories in Brazilian for self-propelled sprayers and seed drills, also destined to the Brazilian market. So here you can see the position of Kuhn Group in the global agricultural machinery context. There's a list of most of our competitors. Then you have approximately the number of employees and the different family of products. There are mainly two groups. The first group with companies that produce tractors, combine harvester, foragers. These are generally very big companies with up to 70,000 employees, and we call them the major company. And then there's another group with the company that produce only tools, self-propelled tools or tools to be used with a tractor. Kuhn is one of the biggest company in that second group. There are also hundreds of other competitors with less than 1,000 employees. So you can see that Kuhn is a manufacturer which proposes as tool manufacturers the widest range of products. This is very important for us to be able to give to our dealer network the possibility to offer for each work in the farm a machine under the same brand. So a look of our R&D organization. We have a R&D budget of approximately 4% of the turnover, over 1,600 patents worldwide. We have 30 people in the electronic department for all Kuhn Group. The Kuhn SANDNER organization, total personnel of 1,300 people. Total R&D personnel, 120 people. The mechanical design office, 60 people. Finite element calculation and simulation, 5 people. And 35 people are working in the testing department. We assemble in the testing department 50 machines per year, 15 new models, which are the priority tests. And we have 3 people working in the test benches and 2 people in the measurement department. Concerning the testing of our machines, the start point was for us that we had a very important limitation with classical tests. The field tests need important human resources for a few number of hours. We have a very bad repeatability due to the driver's driving style and the variability of the field conditions, frozen ground, soaked soil, soft ground. The test benches built with standard mechanical hydraulic components guarantees not enough control of the applied loading and not enough repeatability. So we decided to invest in new technologies to develop our testing resources. MTS is our main partner in that domain. Here you can see our global validation framework and the place from the test benches in that process. So we start, the first step is to design the product with PTC tools. Then we do FE analysis and simulation also with PTC tools. We build the prototype, we do in-field measurements, and then we do tests on the test bench. On the last 3 steps, we do a correlation work. Then we can extract the in-field load cases for cycling loading in fatigue and maximum loading. We do a FEA update, and then we wait the prototype feedback, and we redo a new correlation work. After that, we can do a global and final synthesis with all the data, the FEA results, the customer feedback, fatigue weld capacities, the prototype running feedback, the in-field measurement, and the result from the MTS inertial test rig. We can update the CAD design, and we hope that we can manufacture with confidence. As we have a very limited resources for physical validation, human and material, our workflow is strongly based on numerical calculation. We have a strong interoperation in our workflow between the both worlds: physical validation, test benches, MTS RPC Pro software, and numerical validations, FEA, multi-body dynamic. The numerical validation gives us high added value to physical validation. We use virtual testing coupled with fatigue to understand bed place failures. We apply FEA options to understand failures. We understand the difference between the inertia test bed plate and the real tractor, etc., and other works. So at the end, the goal is to have a better physical validation preparation to perform the test in the best way and don't have to repeat it. Repeating a test is for us impossible with our limited resources. So concerning the test equipment, the first step was for us to create a testing platform with 2 standard actuators from MTS. So we booked an hydraulic power unit with 100 flow rate from 100 liters per minute, 2 cylinders, 2.5 ton and 5 ton with a stroke of 250 millimeters. An MTS hydraulic service manifold and a controller with a controller MTS Flex Test 40. The goal of this equipment is to have our first experience with servo-controlled hydraulic cylinders. With that equipment, we can do, of course, fatigue tests. We validate our finite element calculations. We do strain gauge measurements on the test bench. And as we control and measure both parameters, force and displacement, we can have a good identifications of the crack initiation and so a good determination of lifetime. We can, as we have two actuators, we can also test sub-assemblies. We reproduce in-field solicitations. The test rig is adjusted by strain gauge measurements. We work with equivalent fatigue loading, and we are able to do biaxial loading. The second step for us was to build an inertial test bench to be able to test our carried machines. So the carried machines are the machines for which we have the most difficulties with the repeatability of the field, of the test conditions in the field. So the test bench is constituted by a standard hydraulic actuator from MTS and a custom-made frame from the company CFM Schiller. The test bench reproduces reproduces a tractor. We have two actuators simulating the rear axle from the tractor and one actuator for the front axle from the tractor. There is also a mechanical 3-point hitch to connect the agricultural tool. The principle of the inertial test bench, we do in the field acceleration measurements. We mount on the test bench exactly the same machine with the same acceleration sensor, and we use the acceleration signals to set the test bench. By iteration loops, we set the test bench to have so close as possible the same responses with the acceleration sensors as in the field. To validate the setting of the test bench, we do damage calculations and we control parameters, time signal on service test and then test bench. We control the frequency response, the number of peak. We do level crossing counting, and we compare also the damage. To be sure that the setting is okay, we also often do strain gauge measurements to compare the response on the test bench and in the field. To control the test bench, we use RPC Pro software accompanied by the 793 station configuration software from MTS. The starting package, was constituted by the options Project Manager, Setup, Model, Simulate, Base Test, and the Statistical Trend Monitoring. The use of RPC Pro can be split in 6 different steps. The first step is to record the service data. So we do acceleration measurements for each condition of use on the machine. In that example, on road transport, dirt track transport, and headland. And the acceleration signals are filtered to be compatible with the test bench. The second step is to edit the data. So it's a data processing. It's a data processing of the signals acquired before. For the moment, we do that step on another tool as RPC Pro, and after post-processing, we import the results in the driving computer. So the operations to be done are deleting portions, scaling, resampling, setting the unit, waveform surgery, etc. The step 3 is to measure the system response. So we play with each actuator a white noise in displacement, and we measure the response from each acceleration sensor. The goal is to determine the FRF matrix with the response of each acceleration sensor in relation on each actuator in displacement. The step 4 is to calculate the inverse FRF matrix and to calculate the initial drive. So the data acquired in the first step are used as desired signals. And we transform the FRF matrix to an inverse FRF matrix. This is only a mathematical operation. And then with the desired signals and the inverse FRF matrix, we can calculate a first initial drive. This is our first theoretical initial drive. The step 5, we perform the iteration. So the initial drive, we play on the test bench the initial drive generated before. We measure the response for the test bench for each acceleration sensor, and we calculate an error signal. Then we use the inverse FRF matrix to calculate a correction signal. Then we can generate a new drive, corrected drive, that we can play on the test bench. So we repeat this process loop by loop until we have responses on the test bench so close as possible to the desired signals. So the step 6 is to perform the iteration. So for each condition of use, we have generated a final drive. We play these final drives so many times as necessary to have the total lifetime. During the test, we control, with the trend monitoring, we control the peak values and some statistics values. Okay, look, the goal for us is to progress step by step and to add gradually new possibilities to our testing equipment. So the next important step for us will be to add the missing degrees of freedom to our test bench to have to control up to 6 degrees of freedom. So we can test large working width machine in yaw. We can also test assemblies like sprayer booms. And this upgrade is now in progress. We should be able to do that in beginning 2020. So the other important steps in the future will be to be able to test semi-trailed machines. So we have to add 2 posters and also testing trailed and self-propelled machines. For that, we need to have 4 posters. Okay, thank you very much for your attention.